Okay, guys. Once again, I welcome you all in this video session or in this lecture in which we are discussing about the fundamentals of the manufacturing processes. In the last lecture number two, we started about the manufacturing technology, that how we are giving an input to the uh, of the material, means raw materials, we can say, and then we are using the different types of the manufacturing processes or manufacturing technologies like casting, welding, and the machining operations. Okay, so how we are converting that raw material into the required shape and size. Okay, so that we discussed, and also we started the second unit, which is based on the casting. Okay, so in the last lecture, we discussed about first of all, we discussed the casting definition, that how we are casting basically. Okay, for that we need a mold cavity, and we are pouring the molten material, and then we discuss about the casting terminology. Okay, means exactly when we are going for the casting operations, what are the basic equipments are required. Okay, and how the exactly the casting processes occurs. Okay, so that we have gone through. We also started in the last lecture that about the pattern, that because like as we are filling the mold cavity into the sorry we are pouring the molten material into the mold cavity. So how we are preparing that mold cavity? Okay, for that basically whatever the shape of the casting you needed, same shape, or it depends on the what material you are using. So allowances also we have to take into consideration while making the patterns. So accordingly we are making the patterns, and then we are just filling it, keeping this pattern inside the mold sand. Okay, then the once it is prepared, this mold cavity is prepared. So after that we are just keeping it outside pattern. Okay, then we are filling the molten material. So this is how exactly the casting occurs, and for that we need the patterns. Okay, and we started the pattern allowances as well. So let's start again. I will just brief you about the shrinkage allowance, then we'll move to the other allowances. Okay, and today in this lecture we'll also discuss about the molding sand and their properties. Okay, means what are the basic properties is required. So pattern we have already discussed that these are the this is the this kind of shape, like we have to prepare by using the casting. Okay, so by pouring the molten material. Okay, so exactly same size of the pattern we are using, or it depends that what material we are using. So accordingly that what allowances we have to keep in mind, we have to take that into consideration, and accordingly we are using the pattern. So this is the pattern that is prepared, and once pattern shape is formed inside the molding sand, after that we are keeping it outside. And last time also discussed that this is basically here we are taking a parting line. Okay, so above that there is a core part. Okay, and below that is a drag part. Okay, so this shape, this is a molding sand basically. So this is kept inside the drag part, and above that is also the molding sand, but here it's not visible. But last in the last lecture I completely discussed that thing, so for that you can prefer that one. Okay, so this shape is formed, and once this shape is formed, after that we are just keeping, once this pattern is removed, and we are keeping the core part over there over the drag part, and then we are filling the molten material. Okay, so this is the pattern. Okay, so these are the pattern allowances, like shrinkage allowance, draft or taper allowance, machining or finish allowance, a distortion or the camber allowance, and the wrapping allowance. Apart from this, we have discussed the shrinkage or the contraction allowances in the last time. That whenever as we are filling the molten material. Okay, so molten material means it is in the liquid form. Okay, so this liquid form means if we are talking about the iron, then it is melted at the 1534 degrees centigrade. Okay, and if we are talking about the aluminum, then that is in the range of 900 to 1000. Okay, because there is a different grades of the aluminum. So this is this is a initially it is a liquid. Okay, with respect to time, this is y-axis, we are taking temperature, and x-axis it is a time. So here initially the liquid form. Okay, as we are keeping it, like we are filling it into the mold cavity. So now we are not now we are not heating it from any other elements. So as we are filling it into the mold cavity, now after that it immediately means within a it's the cooling rate is very fast from liquid to semi solid. Okay, then at semi solid, so this is from at semi solid also, like initially if this is the, if this is the like cylinder we have to form, this is a mold cavity. So initially when the mold is filled into that, from the boundary side basically the solidification starts. Okay, so from the boundary line solidification starts and it moves towards the center, it moves towards the center. Okay, so this is, it also takes some time to solidify complete material. So from here to here it will take some time, and after is it will become solid, semi solid, it will take it will take more time. Okay, as comparatively whatever the cooling rate we conserve, we assume from liquid to semi solid, but from semi solid to solid it takes a lot of time. Okay, because it is has to be go into the solid form, so it takes time. Okay, so the allowances that we have to consider during this phase. Okay, so here it from the liquid to semi solid, we are calling it as a liquid shrinkage, because from liquid it is going to the semi solid. It's semi solid because it is suddenly not it's become semi solid at all the complete volume. Okay, it takes some time. So here we are calling it as a solidification shrinkage. And from semi solid to the solid at the room temperature we can say, so it is basically a solid contraction. Okay guys, so these things we have discussed, and I also briefed you about how these allowances are affiliated with the casting. Okay, and the riser. So this is the casting pattern. If we are talking about the casting or the pattern, here it's not exactly the pattern, but to create that casting, to create that mold cavity for the casting. Okay, we are taking the pattern, so that's why I have written over here. Okay, so what we have to take is, if we have to consider the pattern, okay, please keep in mind, if we are if we are making the size of the pattern, then we have to be consider the solidification shrinkage as well as the solid contraction. Okay, now if we are talking about the riser, okay, then we, because riser I discuss very in detail in the first time, first or second lecture, or last time second lecture, that riser is the top part at the mold cavity. Okay, so through which basically as the molten material is coming out, exactly it is we are calling it as a molten material, so that is in the form of liquid and the semi solid. Okay, so if we are talking about the liquid, then that is affiliated with the liquid shrinkage, and if we are talking about the semi solid, then it is, so it is related with the solidification shrinkage. Okay, so please keep in mind this one. So whenever we are designing about the riser, we will consider these two shrinkages or allowances we can say, or if we are talking about the pattern or the casting, then we will consider these two casting sorry, allowances. Okay guys, so please consider keep in mind. Now let's move to the next one, second one, which is a draft or taper allowance. So for this basically like this is exactly the shape that we have to create. Okay, so this is exactly the shape that we have to create. Okay, so what we are doing is initially exactly shape means this is the type of casting we have to prepare. Okay, so what will happen that for an example, this is the molding sand in which this shape is performed, means this shape is we are keeping it inside, and finally the shape is formed. Now as we are filling the mold cavity, means as we are filling the molten material into this cavity, this will be filled, and just assume that after filling the molding mold material, okay, sorry, the molten material, it will become a casting. Okay, because once the pattern is removed, what will become, it will become a casting. So this is, just assume that this is a casting, and now you have to remove this from the molding sand. Now you have to remove it from the molding sand. So if it is sticked with the molding sand, then what will happen, you will try to shake it, or either you will apply some kind of hammer, or you will try to pull it. These are only the options that is available to us, or you will do something else, means it will not be like easily it is coming out. Okay, because whatever the material is there, that will stick to that molding sand is there, that will stick to this surface. So maybe they will try to make the contacts bonding between the molten material and the molding sand. So what will happen that like for one more thing is here, that whatever the dimensions that we have assumed, for an example, if it is casting is expanded, just I am assuming, uh, okay, for an example, that if it is whatever the dimension, like 10, this is of 10 means 1 centimeter we can say, and when we fill the molten material, it is expanded and it become 1.1, this size of the casting become 1.1. So what will happen, there will be a kind of interference fit. Interference means there will be a more force we have to be applied to remove this casting. So what will happen, there may be a damage of this casting, there is a possibility. So to avoid that possibility, to prevent that causes, okay, to prevent this that uh, damage of the material, we are using such kind of patterns. Okay, for an example, if we these kind of patterns, okay, so here for an example, exactly we have to produce this type of the shape, okay, but we will provide some this is kind of pattern initially, exactly the casting that we have to produce of same type. So what we will do, we will provide some kind of taper section over here, not to the casting but to the pattern. Okay, so casting will automatically become like that. So now you can say this kind of casting is formed, and if you will wrap it, or if you will just like shake it, and then we will remove, there will be a no disturbance. If there will be a disturbance or removal of the material where something will happen, then this will be happen from these surfaces. Okay, so there is a one more thing that like how now there is a possibility. Now you can ask me this question, sir, this is exactly not the required dimension, this is beyond the dimension. Obviously this is the beyond dimensions. So what we have to do, we have to go for a machining operations. Okay guys, so please keep in mind this one. Okay, so taper is provided by the pattern makers on all the vertical surfaces of the pattern, so that it can be removed from a sand without tearing away the sides on the sand mold, and without excessive wrapping by the molder. Okay, so this is all the meaning of taper allowance, that why we are providing. Okay, next is the machining or the finishing allowance. Guys, whatever the three allowances that we are going to discuss now onwards, like machining or distortion or wrapping allowance, this is all are affiliated with the draft allowance. For that only, just you can keep in mind that for that only we are using the draft. Okay, now what I have discussed here, that here if this is the excessive amount of the material, then obviously we have to remove and we have to go for a machining operation. So this is the same thing, machining or the finishing allowance. Allowance depends upon the size of pattern and shape of the casting. Obviously excessive size of pattern required as a mass as a material concentration rate. Okay, irregular shapes sometimes causes extra intrinsic geometry of the pattern casting. Means what we have to do is intrinsic means very complex geometry. Okay, so if we have to produce very complex geometry, then for also uh, uh, we have to keep in mind all the allowances which is related with the material. Okay, and accordingly we have to accordingly we have to create a pattern, because like if it is very complex, then it's not like all the time we will invest the money to mold the material. Okay, it will not be like that. मान लीजिए कि means if why we are going for a machining allowance, that we do not have to repeat the pattern, if we do not have to repeat the casting, sorry. Okay, casting means अगर मान लीजिए कि whatever the shape that you have chosen, if it is going मतलब स्मॉल बन जाता है, मतलब उसकी डायमेंशन जो है छोटी रह जाती है, तो फिर प्रॉब्लम होगी. देन अगेन यू हैव टू गो फॉर अ मेल्टिंग ऑपरेशन, दैट यू हैव टू मोल्ड मेल्ट दैट मेटल, एंड अगेन यू हैव टू गो फॉर अ कास्टिंग ऑपरेशन. बट अगर लार्ज साइज बन जाती है, देयर इज नो इश्यू, वी कैन गो फॉर अ मशीनिंग ऑपरेशन. सो फॉर एन एग्जांपल, इफ वी आर गोइंग फॉर अ एक्सेसिव like large amount of the operations, then we will consider like batch production we are going, then we consider little allowances. Okay, because otherwise this slot will be go in west. Okay, and if we are make producing any complex geometry, for that also we are keeping in mind. Okay, so this is the machining allowance. Next is the distortion or the camber allowance. It is just like for an example, if we are producing either U kind of the shape, okay, or V kind of shape, T kind of shape, I sections for the railway tracks. Okay, or like this is a T kind of section that is producing. So what is happening is sometimes it will become like this, it sometimes it will become like this. We call this one as a distorted allowance or distorted pattern. or we call it as a camber pattern. Means it just depend on the shape. What is shape is that whether it's a convex or concave, but here we have given some name. If it is moving towards the larger size, then we are calling it as a, means if this T will become like this, okay, or this I will become like this, then we are calling it as a camber. Or if it is I become like this, okay, or T become like this, so V become like this, okay. Or so similarly, like these kind of geometry can be formed. But why it is actually forming? Actually, when this is basically the casting, okay, and every material, when we are going for a casting, all the metals, it has internal resistance, much internal stresses, and we call them as a residual stresses. Okay, we call them as a residual stresses. So residual stresses is nothing, means it some specific temperature, or we can say like we are measuring, whenever we are measuring this internal residual stresses, we are measuring at a room temperature. So let's take a let's consider that whatever stresses, internal stresses that we are measuring at a room temperature, they are basically the standard in size. Now when you will change, when you will melt the material, so everything has been deformed. Now it was actually the solid, now it becomes liquid. So from liquid it will come to the semi solid, then from semi solid it will become solid again. And we don't know that how the process is going on, if we are applying any heat treatment process or there or not there, okay, or what type of the pattern we are using or in which we are filling. So if we are using this kind of geometries, then there is a possibility that this curve can be deformed like this, okay, towards upside. It's not basically the upside and the top side, but the towards the larger one size, okay, and the small one side. So we are calling it as a distorted and the camber allowances. Because of that it happens. Okay, so what we have to do, if it is actually occurring like this, okay, like this, if it is distortion, then we initially what we are doing is we are using this kind of patterns. Okay, we are using this kind of pattern, so we are filling the molten material into that. So what will happen, initially we have measured the what is the distortion rate of this material, specific material. For an example, if we are using the aluminum, then for the aluminum we have measured, we have checked what is the distortion rate, or okay, distortion rate. So accordingly, now what we are doing, we are making a pattern which is a replica of that object. Means replica means replica of this distorted model. Okay, so if we are keeping these allowances in the beginning only, we are giving the these allowances to the pattern in the beginning only, then final shape will be like this. Okay, and if they, for an example, if there is a camber is formed, okay, due to the allowances, then we are using these kind of geometry. Okay, these kind of geometry. So this is the material is filled into that, and once it will be solidified and become solid, it will become like this. Okay, means whatever the shape, distortion allowances or camber allowances required for this one, we are giving it to the pattern only. Okay, and after that this become like this. Okay, so now you can ask me one question here, that depends that how it is going to be distortion, like this shape can be possible or like this can be possible. So it depends on the material, how it is behaving actually. Okay, so that depends on the material only. Okay, so distortion is due to the internal stresses or residual stresses, we can say. These stresses are causes on the account of uneven cooling rates. Okay, so if we are from liquid to solid, semi solid, it is large cooling rate. So if we are increasing that one, then again there is a possibility to, because we have to produce mass production, so we have to make it cool it very fast. Okay, so for that we have to keep in mind this allowance. Okay, uh, generally it occurs in the bands of U, V and T sections, or I sections, we can say, because it is very important, because I sections generally produced by the casting. So, and that is required in large quantity for the railway tracks, okay, and metro tracks as well. Okay, and many places, at many places. Apart from this, the measure taken to stop bands, which is providing the allowances on the pattern, call camber or the distortion allowances, give enough machining allowances to cover the distortion allowances. Okay, means for an example, like if we are keeping the pattern like this, or if it will not be like if we have means we have to provide it enough allowances to them, okay, so that at the end it will become a straight one, or if it will not, if small mini machining is required, then we can manage with that, okay. Last one is the wrapping allowance. Wrapping means nothing but, wrapping is nothing but like we are just applying the hammering, okay. So hammering means, for an example, like this is a mold cavity, okay. This is a, like initially it is a mold cavity that is made by the pattern, okay. So if this is a small, because this is cop and drag is also there, so this is the molding sand, okay. And this is basically the, this cylinder is basically the we filled the casting molten material into that, so that become casting. So now what will happen, once we will remove, if we want to remove this one easily, then we will provide the hammering on that from all the sides, okay, from top view and side view. Generally you have seen these things, okay. This is very common everywhere, so in other processes as well, okay. So we are just applying that force on that, and it is removed easily. So this is basically the meaning of wrapping allowance, but generally this occurred after complete solidification, okay. So please keep in mind. Now let's move to the next one, which is the molding sand uh, mo- molding sand composition, okay. Then okay, let's complete this one. So here is give me a break. So molding sand composition is molding sand composition means whatever the sand that we are using, it's not a simple sand, okay. We are using a combination of that, so it's not like a simple sand we are using, and it's not like simple sand we are filling into the cop and drag, and inside that we are fixing the pattern, and after that we are wrapping. So once you will remove the pattern, this will cover that space, so it will not be like that, okay. So what is the composition of this molding sand is, for that we are using the base sand, which is very vastly available, so that is a silica sand, okay. Then we are using a mixture of the clay binders. Here two basic clay binders are the kevlonitic solution or the bentonitic solution that is available, or kevlonite we are also calling it as a fire clay, okay. So this is basically the chemical formula for that, okay guys. So clay binder we are using, and why we are using clay binder, because when you will put the binders into that, so they will basically make the bonding between the silica sands, means molecules, that particles, okay, silica particles. And we are adding the moisture into that, so moisture that can be created by the water. So sometimes it is needed, sometimes it is not needed, so that depends, okay. So by the way, other, if it is not needed, then the molding sand is a combination of silica sand or basic sand, we can say, plus the clay binders, okay guys. Otherwise in many times like green sands and loam sands, where we are using the moisture, so that depends what type of the sand we are using. On the basis of this composition only we have divided, we have just named that these type of the sands are available, okay guys. But this is basically the combination. First is silica sand, which is commonly available, okay. Second, we are using the clay binders, because we have to create a bonding between them, and to provide the moisture, because if you will not provide the water, then what will happen, then when you are just using the clay binders, then what will happen, that when it will make the bonding, it will become dry. Means dry means it will become a kind of whatever the shape that you will provide, it will be it will be into that only, okay. So it's like how we are using the sticks, okay, like what that favy sticks, okay, favy sticks or gums that we are using. So just try to assume that your gum is there, glue is there, so you are just mixing it into the sand, and after some time, when with respect to time, it will become dry, so it will get a required shape and size, okay. But we do not want exactly that one, okay. Otherwise that will basically break, that will become brittle, okay. So we do not want exactly that, so that's why we are adding some amount of the moisture or water, we can say, okay guys. So what are the basic properties that is required for the molding sand, okay. So we have to consider that one. So first is the refractoriness. So refractoriness is the meaning suggests that it is withstand with a very high temperature. Okay, generally the silica sand that we are using, it resist means it can bear very high temperature. So we have to be considered, because whatever the molten material that we are using, till now I taken only two example, like of iron, that is of 1534 degrees centigrade, or aluminum, that is of 1000 degrees centigrade maximum. Okay, so it is like this is beyond this also, like at high temperature alloys are there which is melted, and we are making that shape of that. So whatever the shape sand we are using, it should resist a very high temperature. Okay, so that is the properties that is required. Okay, because of that there will be a no fusion. Okay, if fusion means burning will start. Okay, if burning will start, then it will not be a, it will not we cannot fulfill our uh, means whatever the shape that we are going to form. Okay, next is the permeability. So permeability is basically, it is related with the gases escapement of the gases. Okay, so escapement means whenever as we already discussed in the casting terminology, that we are using the gas vents. But uh, what will happen that as we are filling the molten material which is at very high temperature. So if you will just try to find out some videos on the YouTube, it's available. So if you will see that molten material which is completely red hot, okay, through which the gases are removed. Okay, so gases is removed. So these gases will if these gases should not be removed, then there is a possibility of the entrapment of these gases during in the mold. Okay, in the molten material, we can, in the solid, when it will become solidified. Okay, so if there will be an entrapment, then it will form a casting defect. Okay, porosity will be formed, so that will become basically less strength because of that. So what we have to do, we have to remove this whatever the gases is there, we have to remove it. So whatever the capability of to remove this gases, okay, to gas which is evolved, the capability to remove these gases from the molding sand is termed as a permeability. So please keep in mind. Okay, there's a permeability number is also one more term, so I will discuss after this slide. So for the timing, just keep in mind the permeability to capability to remove the hot air or atmospheric gases from the molding sand. That is the meaning. Green strength. So as I discussed that whatever the it's not this aiding the moisture is not necessarily. It depends that what type of the material, molten material we are filling. So accordingly we can manage. So if we are, for an example, if we are talking about the green strength, then it means that it contains, when it contains the moisture. So like when you are filling the molten material. Okay, so is like once the molding this cavity is formed. Okay, so that is basically the mixture of silica sand, clay binders, and the water. So the shape is formed. Now you are filling this sorry, when you are filling the molten material, immediately, because of a very high temperature of this molten material, this mold molding sand, okay, this moisture, whatever the moisture is there, that is completely removed. That is completely immediately that will become a dry. Okay, so if it is become dry, then it should not become a part, matlab, it should not be like break from its boundaries. Okay, otherwise there will be a problem. So whatever the molten material which we are filling, which is at very high temperature, this should be beared, that should be resisted by the molding sand. Okay, so for that only that is strength that is registered by this molding sand, we are calling it as a green strength. Now let's move to the dry strength. All these are affiliated in a sequence one by one only. So green sand, when we are adding the moisture, as the molten material is poured into that cavity, it will soak, it will like this it will become dry. Okay, so that will be that that will be beared by the molding sand. Okay, so that is basically the strength, we are calling it as a green strength. Dry strength, when it become dry, immediately there is a chances of breakage. So if it will not break throughout the molding process, throughout the solidification process, then whatever the strength of the sand, we are calling it as a dry strength. Okay, hot strength is like is immediately as we are filling the molten material, it will become dry. So it is not like that once you will be poured and it will be immediately we are keeping it outside. It's not like that. We are keeping this whole molten material for some time. So if we are keeping it for some times, then definitely uh, the large the temperature surrounding of this molding sand is increases, so there will be no disturbance. Okay, so if there will be a disturbance, then the molten material, which will take some time to become solidified, so if there will be a disturbance, then this mold cavity shape will be changed. So to bear that high temperature, for that the strength is required by this molding sand, we are calling it as a hot strength. Okay, so these are the basic properties. These are basically properties of the material we are talking about. And this is the permeability which is by the molding sand. For that, sometimes also you will see in the books that we are using the porous material of molding sand. Okay, whatever the molding sand that we are using, we are making it as a porous. Okay, refractoriness, that is also the material properties. That material means the sand properties. Okay guys, so these are the properties that is required while forming the molding sand. Okay guys, let's move to the permeability number. Okay guys, I will discuss this one into the next next lecture. Thank you so much. Okay.